Okay, let's resume our discussion of the limits of algorithms. And this time we want to look at intractable problems that we truly want to solve. We saw in the previous video that we can use intractability to protect us. So if we use extra long passwords with lots of different symbols in them, we can protect our passwords from brute force attack. But what about problems that we truly want to solve? One such problem is the Traveling Salesman problem, or TSP. Given a list of cities and the distances between them, find the shortest path, visiting each city once and returning to the start. This is an example of what's called an optimization problem, finding the best possible solution, optimizing the solution. And the only way to really solve this is to use a brute force algorithm. Make a list of every possible path through the cities and then choose the shortest one. But how many possible paths are there? If you have n cities, then there's n ways to choose the first city. Once you've chosen that, there's n minus 1 ways to choose the next city, and then n minus 2 ways, and so forth. And if you work that out, you get the factorial expression. N factorial is n times n minus 1 times n minus 2, and so on, until you get down to 1. Or 100 factorial is 9.3 times e to the 157th, which is a very big number. And in fact, the factorial function, n factorial, is greater than 2 to the n, our standard example for an exponential function. However, we want to be able to solve this problem. Because there are practical applications for traveling salesman problems in networking, in truck routing, and in other disciplines. Fortunately, there are what are known as heuristic algorithms that we can use to solve this problem in a practical way. A heuristic is an algorithm that produces a fast, correct solution to the problem, but it can't be guaranteed to be optimal. You would get an effective, efficient route through the n cities, but it would not necessarily be the optimal route. And we can look at one example of the nearest neighbor heuristic for the traveling salesman problem. It's simply this: at each city, choose the nearest neighboring city as the next city to visit. Here's an example with 4 cities, A, B, C, and D. If you start at A and use the nearest neighbor algorithm, then you get a total cost for your trip as 57. That's pretty good, but it's not optimal, because if you don't apply the nearest neighbor, if you look at all possible paths through those 4 cities, starting at A, then you can come up with a shorter path. So in this case, the nearest neighbor heuristic failed to find the optimal solution, but it gave us a pretty good solution. And that's the idea with heuristic algorithms. We want a practical solution to a problem when an optimal solution is too expensive to calculate. Okay, we're going to break here now, and we're going to do an activity with the traveling salesman problem and give you a chance to experiment with that.